What's going on, guys? Hope you're doing awesome. So in this video, I want to show you how to implement an SVM from scratch. I want to explain the theory behind SVMs because honestly that would make for too long of a video. And even if I did, I wouldn't be able to explain it as well as Andrew Ng, who has 2-hour lectures on SVMs.
Let's say you have a classification problem.
Also, he has pretty incredible lecture notes, and those are really the only sources I've used to learn about how SVMs work. I'll link that in the description if you want to learn about the theory of SVMs. And in this video, we'll focus on how to actually implement it. So from reading the lecture notes, the final result we obtain from all the derivations is that solving this optimization problem and using the formulas that relate W and B gives us the result that we want. And so there are multiple ways of solving the optimization problem. One is using quadratic programming, which is what we're going to do in this video. You can also use the SMO algorithm, for example, just to sort of heads up so you know what to expect from this video. Without further introduction, let's get started with coding it. So what we're going to do is we're going to do well, first of all, we got to do our import. So we're going to use NumPy, import NumPy as NP. We're going to use import CVXOPT. That's sort of for solving the quadratic programming. And then we're also going to use from utils import create dataset. So these are two functions and plot contour. These are two util functions I created. I just put them here. You can check them out in the description link. It will be on my GitHub. But really, this is just for creating sort of a dataset that we can plot in a nice way. And it will be nice to see what the SVM is actually doing at the end. So let's do class SVM and let's define our init function. And we're going to send in a kernel. Let's use Gaussian as default. We haven't implemented that yet, but we're going to do it soon. And then also the C value. So I don't believe I mentioned it, but we're going to implement the soft margin SVM. So sort of the C parameter just tells us how much we should penalize having the sort of misclassifying a point. We're going to set it default to 1. And then self.kernel is kernel, self.c is C. And then let's do the overview, sort of the skeleton code. We're going to have some fit function that we're going to send in x and y. And here we're going to find our alphas. And then we're going to have a prediction. So this will sort of predict each point. And then we'll have another get parameters. And here we'll send in the alpha values. And yeah, that's sort of it. We're gonna have also if name equals main, and then we're gonna run the SVM. So in the fit function here, we're gonna do self.x equals x, self.y equals y. And then we're gonna do m comma n is x shape. So M for the sort of following Andrew Ng's notation. M are the training examples and N are the features. And then we're gonna calculate the kernel. And let's actually do that one because we're gonna use it. So let's do define Gaussian, and we're gonna send in two vectors, x and z, and we're gonna use some sigma. Let's say 0.1 as default. This will depend on the data set, but let's just use that one for now. We're going to do mp.exp of minus mp.linalg.norm and then x minus z. And we're going to do it for axis 1. Then we're going to square this and we're going to divide by 2 times sigma squared. All right, so now we're going to define self.k for the kernel to be mp.zeros, m comma m in shape. And then we're going to do for I in range m, self.k. So we're going to do this, I guess, semi-vectorized, not fully vectorized. We still have one loop, but we've removed one of the loops. We're going to do self.kernel of xi and then mp.newAxis and self.x. So this will, let's see, this will calculate the kernel for a specific training example with all the entire data. So the final shape will be m by m. And yeah, so now that we have calculated the kernel, which is sort of the, the inner product of phi x xi times phi of xj, sort of the notation Andrew uses. And then what we want to do is we want to send in sort of to CVXOPT, and we want to tell it to solve this quadratic programming problem, and so that we can obtain the alpha values. Now the CVXOPT requires it to be on a specific form, and we don't have it on that form, sort of the optimization problem that we saw previously. So we need to do some just reformulation to have it on that form. And yeah, if you have any questions about that, I'll link to a blog post that does a pretty good job of explaining how we reformulate it. But either way, the final thing that we come up with is that P should be CVXOPT.matrix np.outer y and then self.k. Q should be CVXOPT.matrix minus np.ones. And yeah, so I highly recommend that you sort of go through it step by step to see that how we reformulate the optimization problem. But that's really all we're doing here. If you understand the original one, we're only reformulating it so that we can CVXOPT can solve it for us. And then here we're gonna np.vstack np.I of m times -1, and then np.I of m, and then h.matrix np.hstack. Yeah, so the h here is for the alpha values. We require it to be we require the alpha values to be greater than 0 and less than c. And yeah, and then we have a to be CVXOPT.matrix y in shape 1, m, and then d just to have it in to convert it to floats. And then b will be CVXOPT.matrix np.zeros 1. Then we're just going to do CVXOPT.solvers.options and then show progress equals false, just so that it doesn't print unnecessary things. And then the solution will be CVXOPT.solvers.qp, and then we're just going to send in all those that we formulated above. And then self.alphas will be np.array of solution and then x. Yeah, so I don't expect you to follow all of these ones. If you follow the theory, you should then be able to just convert it to in this form, and that's how it results in the code. So what we want to do now is, having the alpha values, we want to get our parameters. And let's see here. So we're gonna have a threshold. Let's set it to 1e minus 4 or something like that. And then we're gonna do the support vectors will be where the alpha values are greater than the threshold, but they should also be less than self.c. So we're sort of using a tolerance value when it's greater than 0. So this, if it's greater than this, then we say that it's greater than 0. And then we're just going to do flatten. So this right here will just be a binary vector, right, for the support vectors that we have. So we're going to do self.w is np dot, and this sort of follows from the formula as well that was given in the lecture notes. So we have x of s, so the support vectors, and then to match the shapes we just take transpose, and then the alphas, similarly the support vectors of the alphas, and then self.y of as well the support vectors. Then we're just going to do np.new axis to have the shapes match, and then self.b will be the mean value of self.y of support vectors. Again, numpy.newAxis minus self.alphas the support vectors, and then self.y, and then lastly, so let's put this on a line like this, and we're gonna have self.k, so the kernel of the support vectors, and then the support vectors in the columns, and then we're just gonna do np.newAxis to not have any weird shapes, and here we're gonna return the support vectors. Now that we have sort of the W and B, just following from having the alpha values from the CVXOPT, then we're gonna send it into predict. So the predict will be yPredict will be np.zeros of x shape 0, right? So we're going to have prediction for each of our points. The support vectors will be self.get parameters of self.alphas. Then we're going to do for I in range of x shape 0. We're going to do yPredict of I is going to be the np sum of self.alphas of the support vectors, and then self.y of the support vectors, and then again np.newAxis. And then here we're going to do self.kernel of xi, comma self.x of the support vectors. And let's see, we're going to have newAxis again, just to have correct shapes. And then in the absolute end, we're going to do, we're going to do return np.sign of yPredict plus self.b. See, here's some error. X, yeah, so we should have, I think we should have self.x here. Yeah, and yeah, so as I said, there's a lot of math behind this. I'm just showing you how to do it and not the theory behind it. And again, I refer you to the lecture notes and drawing. And if you have any questions about the code, I'd be happy to answer them. But these are just sort of how we implement it. Yeah, let's also define, so we can use some other kernels. We could use the linear kernel. And for R in this case, just to have the shapes match up, we're going to have x comma z transpose. And then let's say we have a polynomial as well. And you can define more kernels, obviously, but we're just going to use the polynomial, and we use a default polynomial of degree 5. And we're going to return 1 plus np dot of x z transpose, and then take this to the power of p. And let's see that we should now be ready to sort of get our data and train. So let's do np.random seed 1 just to have reproducible results so that you can sort of get the same. And let's do xy is create data set, and let's pick 50 points. And then we're going to do SVM is SVM of kernel equals Gaussian. So that's sort of default, so we wouldn't have to send that in, but svm.fit x and y, and then yPredict, let's do svm.predict x. And yeah, we can sort of do print f accuracy is, let's do sum y equals y prediction, and then divide by the total examples that we have. And then also let's use the function, so plot contours x, y, and we're going to send an SVM here as well. You're going to see what this does in a second. Plot contours like this. And yeah, so let's run this. Can't import plot contour. Okay, so it should be like this, and hopefully this works now. So we get, yeah, accuracy is 99%. And then, so what I did with those functions right there is that, see, I don't know what is printing right now. It's probably from this one. Yeah, so remove this print here, and let's rerun it. And let's bring out the plot. So right here, let's see. So right here. So as I said, this is sort of the contour plots. Yeah, and I plotted a bunch of them. Yeah, so this is how the data looks like, the one we generated. And having the SVM predictions, the decision boundary looks like this. So it can be sort of interesting to see how the SVM does its prediction, and we can sort of, you can, let's see, we can use a polynomial instead. We can run it and we can see that, okay, so it takes a while. We can see that this is how the polynomial looks like, and if we would, decrease the power of it, then we would probably get something that looks more linear, I guess. Yeah, and yeah, you could increase it as well. And I don't know, 5 seems like a pretty good result. And then we can do also, the linear one, and this should be pretty linear. So let's see. Yeah, so we get a very linear decision boundary. So I think that's it for SVMs. If you have any questions, leave them in the comment. Thank you so much for watching the video, and I hope to see you in the next one.